So today we are going to learn how to write the main VHDL model MVM and test bench VHDL model TVM for a full adder system using half adder as a component, that is structural modeling style. So we are going to refer to two block diagrams. This is the first one. As we see, full adder has three inputs AI, BI, CI and two outputs carry and sum, which are named as carry underscore full adder and sum underscore full adder. And the truth table here shows the three inputs along with the two outputs. Because we want to implement full adder using half adder as a component, we have to express full adder as a combination of half adder and OR gate as shown. So in structural modeling style, the full adder is known as top level entity or parent entity, while the half adder and OR gate are known as components or child entities. So as we see here, this full adder as represented by the dotted rectangle is a combination of two half adders, that is HA1 and HA2, and one 2 input OR gate. So while half adder is called as a component, HA1 is known as the first instance of the component half adder and HA2 is known as the second instance of the component half adder. Now it is important to note how the three inputs of full adder AI, BI and CI are connected to the two instances HA1 and HA2, and at the same time how the two instances and the OR gate, they generate the carry and sum outputs. So we can see here that each instance of half adder, that is HA1 and HA2, has two inputs x1 and x2 and two outputs C1 and S1. So C1 is the carry output of half adder and S1 is the sum output of half adder. So these two are x1 and x2 inputs of HA1, carry output of HA1, sum output of HA1. Similarly, here we have the inputs x1 and x2 of HA2 and the carry and sum outputs of HA2. Here we see that the inputs of full adder AI and BI are connected to x1 and x2 inputs of HA1, while the third input CI is connected to x2 input of HA2. Similarly, we see that the sum output of HA1 is connected to x1 input of HA2, while the sum output SA1 of HA2 forms the sum output of full adder. Similarly, the carry output of HA1 and carry output of HA2 are logically OR together to generate the carry output of full adder. Now we see here that carry underscore HA1 is an intermediate signal which is defined to show the connectivity between the carry output of HA1 and the first input of OR gate. Similarly, sum underscore HA1 is another intermediate signal which is defined to show the connectivity between the sum output S1 of HA1 and the X1 input of HA2. Here, actually, although I have shown, there is no need of defining this signal sum underscore HA2 because the sum output of HA2 is directly forming the sum output of full adder. There is no need to define. So intermediate signals are to be defined only in the connections between the output of an instance and the input of another instance. Okay, so having said this, we will directly learn how to write the main VHDL model of full adder. So what basically we are going to do is, we are going to first write the main VHDL model of full adder, and which will involve the library statements, the entity declaration, and the architecture body. So architecture body of the top level entity or parent entity, um, it consists of four important steps. First is component creation. Second is um, defining the intermediate signals. Third is component instantiation. Fourth is port mapping. So the first two steps, that is component creation and defining the intermediate signals, are done in the declaration section of architecture body of the parent entity, while component instantiation and port mapping are done in the logic section of the architecture body. Port mapping is basically done to indicate which signals are connected to which inputs of the instances, and which outputs of the instances are connected to either the inputs of other instances, or how they form the outputs of the top level entity or the parent entity. Once we have completed these four steps, then we have to write the model for each component we have created in the architecture body of top level entity. So here we have only one component half adder, and we have two instances of that component named as HA1 and HA2. So we have to write the library section, entity declaration, and architecture body set for the component half adder. Having said this, we will directly start creating the models in Xilinx ISC. File, new project. We'll give the name as FA using HA, Control A, Control C, next, next, finish. Keeping the tool in implementation mode, select target line, right click, new source, select VHDL module and paste. Reselect VHDL module, click next. Change the architecture name to entity name underscore ARCH. Now as per our block diagram, for the top level entity full adder, AI, BI, CI are the three 1-bit inputs, while carry underscore full adder and sum underscore full adder are the two outputs. Although we have written the carry output as carry underscore full hyphen adder, we cannot use hyphen because hyphen is not allowed as a special character in the language. So we will use carry underscore full underscore adder and sum underscore full underscore adder. First input AI, second input BI, third input CI, and we have carry underscore full adder, or we can even say underscore adder, and we can have the second output as sum underscore full underscore adder. Next, finish. Deleting all comments. As said earlier, we'll go to the declaration section of architecture body, and we will create the component with the name HA or half adder. The syntax: component space component name, which is HA, is port. Now, as seen in the block diagram, the half adder has two inputs x1, x2, and the two outputs c1 and s1 representing carry and sum. So we will define as x1 comma x2 space colon the direction in, that is input, and the data type standard underscore logic semicolon. Similarly, the carry output, some output, space colon, the direction out, that is output, and the data type standard underscore logic. So because this is the last signal declaration, not put a semicolon, close parenthesis semicolon, and instead of writing component space component name, we'll write, I'm very sorry, instead of writing end component name, we have to write here end component. In entity declaration we write end space entity name semicolon, but here we write end space component. So from line number 16 to 23 we have created the component called as HA. Next step is we are going to define all the intermediate signals. So as per this block diagram, we have three intermediate signals: carry underscore HA1, sum underscore HA1, and carry underscore HA2. So the syntax is signal space signal name. So it is carry underscore HA1. Then we have carry underscore HA2, and we have sum underscore HA1. So the first two steps, that is component creation and defining the intermediate signals, is over. Now we go to the logic section and implement the remaining two steps, that is component instantiation. Syntax for component instantiation and port mapping is done on the same line. The syntax: instance name space colon space component name space the two words separated by a space, port space map, and then the parenthesis in which we write the connectivity signals separated by commas. So we can write it like this: instance name space colon component name, then port space map, and then here we have to follow the order of the signals in component, that is x1 then x2 then c1 then s1. So x1 x2 c1 s1. Okay, we'll comment them. So instance name is ha1 space colon component name is ha, and then ports space map parenthesis. So here we have to write which signal is connected to x1 of ha1, comma, the signal connected to x2 of ha1, comma, the signal connected to c1 of ha1, comma, and signal connected to s1 of ha1. According to block diagram, we can see that ai is connected to x1 of ha1, bi to x2 of ha2, carry underscore ha1 to c1 of ha1, and sum underscore ha1 to s1 of ha1. It will be ai comma bi comma carry underscore ha1 comma sum underscore ha1. Okay. Repeat the same for the second instance. Instance name is ha2, and sum underscore ha1 connected to x1 of ha2, ci connected to x2 of ha2, carry underscore ha2 connected to c1 of ha2, and sum underscore full adder connected to s1 of ha2. c1 ci carry underscore HA2 and sum underscore full adder. So on line number 31 and 32, we have implemented step number 3 and 4, that is component instantiation um, and port mapping. Now we have to define that the carry output of full adder is a logical ORing between the individual carries of HA1 and HA2. So before we exit the architecture body, we will write carry underscore full underscore adder is assigned carry underscore HA1 ORed with carry underscore HA2 semicolon. Okay. So thus we have completed the main VHDL model for full adder, wherein we have expressed the full adder as an interconnection between the two instances of half adder HA1 and HA2, and also one two input OR gate. Now, as said earlier, we have to write the model for the component half adder. So we need library section which we can copy paste. Then we will write the entity declaration for the component half adder as entity name, which is same as the component name, is port parenthesis x1 comma x2 space colon direction in, that is input, std underscore logic semicolon c1 comma s1 out standard underscore logic no semicolon and entity name HA. Thus entity declaration is over. Now we'll write the architecture body. Architecture HA underscore arch of HA is architecture begin. Here we will express the carry output as an ANDing between x1 and x2 and the sum output as an XORing between x1 and x2. C1 is assigned x1 and x2 and S1 is assigned x1 XOR x2 semicolon and HA underscore arch. Let us see after synthesis what errors we get. Undefined symbol carry underscore HA1. So we have not defined a data type. So the syntax for signal declaration is signal space signal name colon data type. So we have to write colon std underscore logic. Control S, resynthesize. Parameter sum underscore full adder of mode in cannot be associated with a formal port of mode out. Okay. So on line number 10 and 11, the outputs carry and sum have been defined of the type in. Okay, change it to OUT. We are also editing. That means we have made a mistake while creating the MVM, wherein we have defined a direction of carry and sum as input and not output. Again, Control S, synthesize, run. Successfully synthesized. View RTL schematic, block diagram, go inside zoom to full view. This is how it is implemented. Technology schematic, double click, zoom to full view, LUTs are implemented. Now we have successfully done the synthesis of MVM. Now we will do the simulation of TVM. So first, creating the TVM, change the tool from implementation to simulation mode. Target line, right click, new source, VHDL test bench. Copy the name from here, paste it here, underscore TB, test bench. Next, out of the two, we want to simulate the top level entity, that is full adder. So selecting FA underscore using underscore HA. Next, finish. Deleting the comments, deleting the clock period statement, deleting the clock generation process, delete, and here we have to write three processes. As we see in the truth table, the inputs A, B, and C are changing from 000 to 111. So we can either write, so we have to write three processes basically. And we see here that AI is 4 zeros and 4 ones, BI is 2 zeros and 2 ones, and CI is 0 and 1. Which means that when the signal AI completes one cycle, BI completes 2 cycles, and CI completes 4 cycles. That means the signal BI has double the frequency that of AI, and CI has double the frequency that of BI, or 4 times the frequency that of BI. So in VHDL, we cannot define frequency directly, but we have to define it in terms of the time period. So let this process be the process for the first input AI, and we will say AI is assigned not of AI, wait for 100 nanoseconds. So signal AI will have a time period of 200 nanoseconds and frequency will be 1 over 200 nanoseconds. Signal BI will have a time period of 100 nanoseconds, and CI will have a time period of 50 nanoseconds, thereby making CI 4 times the frequency of AI and BI twice the frequency of AI. So we'll copy this process, paste it 2 times. Second process is for BI. So BI is assigned not of BI, wait for 50 nanoseconds. Third process is for CI. So CI is assigned not of CI and wait for 25 nanoseconds. Expand, select the TVM, expand, simulate behavioral model, float, zoom to full view. Now we can see here that the first combination available is A equal to B equal to C equal to 1, and last is triple zero. So as per truth table, the combination should go from triple zero to triple one, but in the simulation it is going from triple one to triple zero. The reason is that in the TVM we have initialized AI, BI and CI to 000. So when the process runs for individual inputs AI, BI, CI, the value is toggled. So initialized to 000, uh, it is modified to 111. So what we will do is that we will close ISIM. We will change the initialization of AI, BI, CI to 1, 1 and 1. Control S, check syntax, simulate behavioral model. So AI, BI and CI going from triple zero to triple one, and the outputs we are getting are as per the truth table defined. Okay, thank you very much.